and it has a fundamental period 2 pi. Okay. Okay, so and we leave the value of this periodic signal to be arbitrary when x is equal to the integral multiple of pi. Okay, so but still you can assign value to f of x when x equal to minus pi and 0, but still remain to keep that f is a periodic function. Okay, and so that means where f can be arbitrary. Can be arbitrarily defined. Okay, at x equal to 0 and pi. Okay, and we have shown the trigonometric Fourier series generated by this f. Okay, it is that, and because that this is we have seen that this part is an odd function, so we know that. Okay, so the trigonometric Fourier series is a series sum of sine function. Okay. Now, so to apply our representation theorem, we see that things we check f is piecewise continuous. Right? Okay, and so you see that okay, so f is piecewise continuous. Okay, so when we look at one period from minus pi to pi, you can one okay, so this is one assignment for the value of the periodic function at multiple integral of pi. Okay, so you see it is periodic. Okay, still periodic, and you can see that it's piecewise continuous, of course. and has a left-hand derivative and a right-hand derivative. All right, at each point x at each point of minus pi and pi. And the left-hand derivative and right-hand derivative are all equal to zeros, okay, because they are constant. So you can see they are all zeros. Okay. So by theorem 11.1.2, so by this theorem, okay, we have the periodic function is equal to, so we know that this trigonometric Fourier series will converge for every x, right? We know that this series will converge for every x, and it's equal to the function value okay for all x in R, which is not which is not equal to integral multiple of pi. Okay. Okay. And the series is obviously okay equal to half 1 plus 1 minus 1, which is 0 when x is equal to n pi. Okay, so as we know, this series converges every point, and for x is equal to an integral multiple of pi, then it is equal to the half of the sum of left limiter and the right limiter. But as you can see, for example, at 0, the left limiter is minus 1, but the right limit is 1. 1 plus minus 1 is 0, divided by 2 is 0, 2. Okay, so that so the series, if we, so the series sum is a figure. So the figure is that. So they coincide. Okay, but the value is always 0. Okay, all right, so this is okay. So the red figure is a figure of this series sum. Okay. Now we will prove A theorem which will be useful later on is called termwise differentiation of trigonometric Fourier series Okay. All right. So we let f be a differentiable periodic function okay, a differential periodic function with a period 2 pi and whose first derivative. So differentiable means that its first derivative always exists at every point. Okay? Differentiable means. So its first derivative f prime is piecewise continuous. Okay? Minus pi to pi. Okay? So first of all, we know f is differentiable periodic function. Okay? So the case is that if a periodic function can be represented by, so in this case, right, you see that any differentiable function is continuous. Okay? All right, so f is continuous. The second, because it has first derivative, right? Because differentiable. So it has left-hand derivative and right-hand derivative at every point. And in this case, left-hand derivative and right-hand derivative are equal. Okay? Right? So in this case, then f of x can be represented by its trigonometric Fourier series at every point. Okay? Because f is continuous. Right? So we know. So let me see. So that this implies by theorem 11.1.2 that f of x is equal to a0 plus summation and from 1 to infinity an cosine nx plus bn sine nx, okay, for all x in R. All right? So it's very strong, right? So we have this one. Okay, in this case. And we know how to compute the coefficient, right? Because this coefficient is generated by this periodic function. So we have. And now, our question is that, is f prime of x, okay, equal to, because it's differentiable, right? So this periodic function has derivative, the first derivative at every point. Okay, so our question is, if if the derivative, the first derivative of f of x at x equal to the derivative here. But you know the derivative of a constant term is 0. So now so our question is that, can we just do the term-wise differentiation? Okay. Can we do that? Okay. Yeah, in some case, not always. Okay. Very good. Yes, under certain condition. Okay. So we try to find that condition, okay, as broad as possible. Okay. Okay, so to answer this question, we have two terms. Still, we have convergence problem to solve, saying that when we do the term-wise differentiation, all right, this series converge. Okay, so we have to answer this question. And the second is the representation theorem. Once it converges, then whether the equality is true or not. So we still have a convergence problem as well as representation problem again. Okay? Again. So the additional, so we need additional property. This additional property is here. So furthermore, okay, assume that f has a left-hand second derivative and a right-hand second derivative. Okay, at each point of minus pi to pi. Okay, i.e., so let me say that f prime, the first derivative, has a left hand derivative. Because the second derivative is the derivative, the first derivative of the second derivative of f is just the derivative of the first derivative of f. Okay, so the f prime has a left-hand derivative and a right-hand derivative. Okay, at each point of is that okay? So when we say f, the original periodic function, has a left-hand second derivative and a right-hand second derivative at every point of this one period, means that the first derivative of f has a left-hand derivative and a right-hand derivative at each one. Now, okay, so in this case, so immediately we know, okay, immediately maybe I use another color, green, okay. So now as we assume here, the first derivative f prime is piecewise continuous, and f prime has a left-hand derivative and a right-hand derivative. So now we can apply theorem, the representation theorem, 11.1.2 again, and we say okay. Now this time, let us say alpha 0 plus summation n from 1 to infinity alpha n cosine nx plus beta n sine nx, okay, is equal to f prime x plus f prime x minus plus f prime x plus. Okay. Okay. And I know that alpha 0, the coefficient, should be computed by using a prime. In here, the coefficient A0, AN, BN should be computed from the original periodic function f itself, okay, by using the Euler formula. Okay, so I hope you still remember them, right? So by Euler formula, you have that. So this is what we have. Okay, right. So from the given premises, we know these two results. Okay, and with that, the conclusion is here. Okay, then no, yeah, okay. So then so now our question, then we first answer now, then the series of termwise differentiation okay, which is summation m from 1 to infinity d to x ak cosine an cosine nx plus Vn sine. Okay, so the series of termwise differentiation converges, right, to the average of the left hand and right hand derivative of a prime. Okay, at every point. Okay, x in minus pi to pi. All right, and in particular, we have. So this is the convergence problem has been solved, right? So we answer the convergence problem that okay, this series of termwise differentiation converge at every point. Okay, and the sum is equal to this one. Okay, and the representation theorem and the derivative is equal to okay, for all points x, where the first derivative f prime of f is continuous. Okay, so the representation theorem is true when f prime, when the first derivative is continuous at x. Okay, so the answer is that well, it may not be true for all x in the real line, but this will be true when f prime is continuous at x. Okay. Okay. Any questions before I give proof? All right. So the proof here. First of all, the alpha 0 is 1 over 2 pi from pi to minus pi f prime of x dx. Okay? So look at, because this representation, this is follow from theorem 11.1.2, right? So we have that. Okay, so this is equal to this one. And, okay. And this trigonometric Fourier series is generated by f prime. By f prime. And we will see that alpha 0 is equal to the integral. So by the, I think by the second fundamental theorem of calculus, we know this is f of x of pi and minus pi. Okay, so this is 2 pi, f of pi minus f of minus pi. Okay, but f is a periodic function with a period 2 pi. So these two values are the same. So this is 0. Okay, this is 0. For alpha n, now we write, and for n greater than or equal to 1, we compute alpha n, which is f prime of x cosine nx and the dx. Okay, so we use the first derivative to compute the coefficient alpha n. Okay, and we can use integration by parts, so that this becomes 2 cosine nx pi minus pi plus n and the pi minus pi f of x sine nx and dx. Okay, so this is by integration by parts. Okay, so by integration by parts we have that. Okay, and look at here. Cosine n of x has a period 2 pi. F of x is a periodic function with a period 2 pi. Okay, so this term is equal to 0, right? Is 0. Okay, all right. And here, now what is that? What is that? This is just Bn, right? The coefficient, okay, in the trigonometric Fourier series generated by the original periodic function f. Okay, so this is Bn. Okay, this is Bn. Oh, I'm sorry, pi. Yeah, so it didn't have. Thank you. So, okay, yeah, thank you. So it's MBN. Yeah. And beta n, 1 over pi, f prime of x, sine nx dx equal to, so apply integration by parts again. So this is f of x sine nx pi minus pi minus n 1 over pi f of x and the cosine nx dx again. So this is an. So we have minus n of an. Yeah. Okay. Okay. All right, and so from the green part here, from the green part, we know that so now summation n from 1 to infinity, and alpha n is alpha 0 is 0, so 0 plus, and here is n bn cosine nx minus nan sine nx. Okay? So this one is equal to 1/2 of f prime of x plus the right hand limit and the left hand limit. Okay, for all x in R. Okay, so that is what we have. But note that the derivative of a0 is 0. Okay, and the derivative of an cosine nx is equal to minus nan sine nx, and the derivative of bn sine nx is equal to n bn and cosine nx. Okay, so that is from the derivative of sinusoidal function. Okay, and so from this discussion we know that this is actually the d dx a 0, and this term is equal to d dx a n bn sine nx, and this part minus n is equal to d dx an cosine nx. All right, so So finally, we have n from 1 to infinity d dx an cosine nx plus bn sin nx is equal to 1/2 of f prime x okay. All right, so we proved the convergence of the series of termwise differentiation. Okay, because they are equal. So this series converge for all x in R. Okay, to this way. And this is equal to f of x, f prime of x. Okay, when and f prime is continuous. Okay, at x. Okay, so this is the end of the proof. Okay. Okay, so the effort we have done here is to establish that this trigonometric Fourier series generated by f prime is just the termwise differentiation of the trigonometric Fourier series generated by f. Okay, so this is the key, right? We established. Okay, so later on, when we consider differentiable periodic functions such that its first derivative is piecewise continuous, and this periodic function has left-hand second derivative and the right-hand second derivative at every point. Okay, in that case, then we can do the termwise differentiation for this Fourier series. Okay, and the termwise differentiation, all right, of the series of termwise differentiation converge really for every point. Okay, and well, converge to f prime of x when f prime, yes, the first derivative f prime is continuous at x. Okay. So this is very convenient, right? It's very convenient. So once a periodic function, we find the Fourier series expansion of a differentiable periodic function, then its first derivative can be obtained basically from termwise differentiation. Okay, termwise differentiation. Basically, when x is at all points such that the first derivative f prime is continuous. Any questions? Okay, so now, we finished the long first section, yeah. Okay. All right, so now now we will consider so-called half-range expansion. Okay, there are two ways of. Okay, now in the first section we consider periodic function with period 2 pi. But a periodic function can have arbitrary. We can consider periodic function with arbitrary period, right? So so let f is a periodic function. Okay, with a period p equal to 2 times L, which is piecewise continuous. Okay, in one period, and has left hand and right hand derivatives at each point of this one period. Okay, so when we consider periodic function with period p, which is equal to 2 times L, now by changing variables x equal to p 2 pi and v here. Now period is 2 times L, so we want to turn such a periodic function with arbitrary period into a periodic function with a period 2 pi. Okay, because in the first section we consider a periodic function with a period 2 pi. Okay, so this is L divided by pi and the v here. Okay, so that f of x, okay, the original function is we can, okay. So by using change of variables, the original function is a function of x becomes function of v. Okay. So this is the function of v here. All right. So you can think about that. This is a function. Okay, and then we call this is as a GV. Okay. So GV is a periodic function. All right, with a period 2 pi. Okay, so now by using change of variable, this is become to G of V. Okay, and it's a periodic function with a period 2 pi. Okay, which is piecewise. So it's just like when you look at the graph of f and g, you can see that depends on the ratio. The graph you may dilate it or shrink it, right, along the real line. Okay. So that this new periodic function is still piecewise continuous, of course. Okay. I hope you have the idea of geometry, and by this ratio you you either compress the diagram or dilate the diagram, right? All right, so which is a piecewise continuous, which is and in minus pi to pi, okay, because this period becomes to this period, okay, and has left hand and right hand derivative at each point of minus pi to pi. Okay. So these two properties remains. Okay, remain. So we have that, and so now by theorem 11.1.2, now we have okay, so we have A0 A0 plus summation m infinity an cosine mv, okay, plus Vn sine mv, okay. So we have that whenever f is continuous, okay, at v and which is okay. Oh, sorry. Whenever G is continuous, okay, at V, okay. So this is from our representation theorem, okay. So GV, this gives us that at V. G is continuous at V means that F is continuous at pi x, okay. All right, so now, okay, so I hope you understand that everything is okay. And the coefficient, so where we compute the coefficient, well, A0 CV, okay, because that the coefficient is computed by the G function of V, right? Okay, and so by substitution, this is the G function is f of V, dV here, because GV is obtained by doing the change of variable. Okay, so we have that. Okay, and when you do that, you use the change of variable again, right? So what is that? So this is become 2. So when you do the change of variable, you set x equal to as before. So dx is equal to L pi and dv here. Okay? And so you have 2 pi. Okay, and the v. So the pi here becomes 2L and minus L here. Okay? And you have f of x here. And this one you have pi and L and dx. Okay? Get it? So that, okay. All right, so you have 2L. Okay. So A0 is obtained by 1 over 2L. 2L is the period of the periodic function f of x. And you integrate f of x over 1 period from minus L to L. Okay, so A0 is here. And what is AN? Okay, the AN, that 1 over pi minus pi, GV, dV, right? Sorry. Cosine and V dV here. And so this is, you do the f of L pi V cosine mv and dV. And we do the same change of variable. Okay? So when we do the same change of variable, we have 1 over L minus L, f of x, and we have cosine. So we have cosine n pi x divided by L. Okay? And dx. Okay? But the same change of variables. All right, because v, when x is this one, v is equal to x. So that's why we have this here, because v is equal to pi x divided by L. Okay, so the AN can be computed directly from f of x, but you have to use cosine 2 pi x divided by L. Cosine n pi x divided by L. Okay, and the Bn again sine mv dv. So this is FL pi v sine nv dv. So this is 1 over L minus L, f of x sine L m pi x and dx. Okay. All right. So finally, so that f of x is equal to so that Okay. All right. And here A0 plus cosine n pi x divided by L plus Bn pi x divided by L. Okay? Because of this, so we substitute v equal to things v equal to pi x. Okay, so f of x actually equal to this trigonometric Fourier series. Okay. Okay, and f is continuous at so and when we go back, so I think oh, at the x, sorry, just x. Yeah, because we have already do the contraction or dilation by using this ratio. Okay, so yeah, so you have this correspondence. So I have to write that. Okay. And if f is not continuous at x, then this series also converge. So actually, maybe I write here. So this series actually is equal to okay. So actually, in general, maybe I so note that then I have to say so. So my conclusion is that A0 plus summation n minus 1 infinity of an cosine n pi x divided by L plus Bn sine pi x divided by L is equal to 1/2 of f prime f plus f minus, okay, for all so in R, okay, and it is equal to f of x when f is continuous at x. Okay, and so this one, this is called the trigonometric Fourier series. All right, generated by f. Okay, so we call it. Okay. And the coefficients A0 is computed by f of x directly over one period. And the an, bn are also computed by using this formula. So this formula is also called Euler's formula in general. Okay. Any questions? Right. So if no questions, then we will take a break up to 2:30. Okay. Yes, yes.应该是不会吧？哦，应该还是可以吧？ Okay. Well, we will consider two special cases. All right. One is that f of x is almost even. Okay, I use almost even. Means that f of minus x equal to f of x. Okay, for almost all x in R. Okay, remember I have taken an example of the clock signal, right? And as you can see that except the integral multiple, all right, the m pi, that we can arbitrarily assign values for the periodic functions. And when we arbitrarily assign the value of function, then the periodic function may not be an even or odd function. Okay, may not. The reason you see here. So let me demonstrate the idea. Okay, so when we look at the periodic function of x, except integral multiple of pi at the point, except the point which are integral multiple of pi's. Okay, then it is an odd function, right? But when you assign value, for example, say, let me say here. Now, okay, then in this case, the f of x is not an odd function. Why? Because f of minus pi, all right, is not equal to minus f of pi. Why? Because f of pi and f of minus pi are equal to each other. Well, maybe I assign here this is 1/3. Okay. Right. So this is 1/3, but this is minus 1/3. Of course, they are not equal, right? They are not equal. So it's not an odd function. Okay. And of course, it is not even, right? Because this part is not even. But so in this assignment, so that now I will say, so f of x is not an odd function. Okay, so it's not an odd function, but an almost odd function. So when we say almost, it means that we can extrude the point in a set. The length of this set is 0, right? Okay, we define almost. Okay, so if we exclude the integral multiple of pi, include those points, we just ignore. Okay, then the function is odd. Similarly, so we say f of x is almost even. Okay, if you have a symmetry like this one for almost all x in R. Okay, so it means that for all x in R, except for those points in a set, the length of that set is 0. Okay? So that. All right. So in this case, the Fourier series, right? Then we compute the Bn. So Bn is and the f of x sine and x dx. Oh, by the way, I forgot to, I'm sorry, I forgot to, L. That we consider periodic function with arbitrary period, okay? So this is f of x and sine pi xl dx. Okay. Now this one is an odd function. Okay, this is an odd function. And this one is essentially even. Okay, so this is an almost even function. Okay. All right, so together this has become two almost odd. Okay, it's almost odd. And when you integrate almost odd function over minus L to L, then the value is 0. Okay. If you have any, okay, let me do it. All right. 0 to L, f of x sine. I'm not sure. Do you have this kind of experience in calculus? Do you discuss even function and odd function before in calculus? So you know that this fact, right? Any question? Do I need to show why this is equal to 0? Not necessary. Okay, good. Yeah, don't hesitate if you need me to do it. Yeah, I will do. Okay. All right, great. Okay, so this is 0, of course. All right, so this is so that f of x. Okay, so I will use this notation. Okay, to show that this is equal to a0 plus summation n from 1 to infinity an cosine nx. Okay. Oh, I forgot. I'm sorry. Every time. Okay, this one. So all the sine term disappear because Bn is 0. Okay, so we have that. And in this case, that you can absorb n0 into the sum. Okay, so you start n equals 0, and an cosine pi x. Because when n equals 0, cosine 0 is 1. Okay, it's a constant function, so you can absorb it into it. Okay, so you have a cosine Fourier series like this one. Okay, this is okay. So when f is almost even, okay, so that you have that. Of course, in this section, all periodic we consider is piecewise continuous and has a left-hand and right-hand derivative. Have the left-hand derivative and derivatives. Okay, so we have that. So that the premises in theorem 11.1.2, okay, are true. Okay. Okay, and so this symbol means that this series is generated by f of x. Okay, and okay, so well, so maybe I say at least this one is absolutely integrable over minus LL. Okay, at least. All right, so so we can simplify the first series. Okay. Oh, yeah. The second case is that f is almost odd, which means that f minus x is equal to minus f of x for almost all x in R. Okay, so this is the odd, is almost odd. Then in this case, for n greater than or equal to 0, including 0, right? Oh, by the way, we have okay. Sorry. So A0 is 0 because the integrand is almost odd. Okay, and for n greater than or equal to 1, an so it's n pi. Okay. Okay, so this is an even function. And this one is almost odd. So together, this product is almost odd. Okay. So the integrand is almost odd. And so this is 0. Okay. And so in this case, we have only sine function. Okay, so we have only sine function here. And Bn, okay, f of x sine m pi. Okay, here. And of course here A0. And the An. Okay. Yep. So there are these two cases we have. Okay, and there is a simple theorem we call linearity of Fourier series expansion. Okay, so let f and g be two periodic function with a period p equal to 2L, such that they are absolutely integrable, okay, over mass L to L. Okay, so now the Fourier coefficient of a linear combination of f and g. So it's alpha f plus beta g. Alpha times f plus beta times g of f and g. Okay. Okay, is the same linear combination is the same linear combination of the corresponding Fourier coefficients. All right, so so that this shows that so if f is generated by a0 plus summation n from 1 to infinity, and bn, oh, sorry, an cosine m pi divided by L x plus bn sine m pi divided by L. Okay, so the f is here, and the g, okay. Okay, so this one, this trigonometric Fourier series, this Fourier series is generated by f, and this Fourier series is generated by g, because both of them, okay, are absolutely integrable over one period. Okay, so this one. And this implies that alpha f plus beta g. Well, if we compute ABCD is 0. Okay, plus F E F G H E and H N. Okay, and this is the Fourier series generated by this linear combination. Okay, implies that En E0 is the alpha An alpha 0 plus beta C0. Okay, and En is alpha An plus beta Cn, and the Hn is alpha Bn plus beta Dn. Okay. So this is the meaning of the theorem here. Okay. All right. Now, we have to check one thing. When f and g are absolutely integrable over this period, then any linear combination is also absolutely integrable. Why? So things right? So we integrate the absolute value of this linear combination over one period. All right? So that then by triangular inequality, we know this is plus okay, because the absolute value of the sum of two numbers is less than or equal to the sum of the absolute value of individual number. Okay, so we have that, and this is of course is finite. Okay, because this is finite because f is absolutely integrable. And this is also finite. So we have that. Alpha f plus beta g generate a trigonal metric Fourier series. Okay, so it generates a and this series, we just say E0 plus summation, okay, En cosine pi Lx plus Hn sine. Okay, so it now where E0 by definition It's okay, by definition, right? Is this integral, okay? And bilinearity of a definite integral, we know this is alpha. Okay. Okay, so this is bilinearity of the integral. And so this is alpha, and this is A0 and the beta, and this one is C0. Okay. This is 0. Okay, so E0 is equal to alpha times A0 plus beta times C0. Okay, right, and the En, oh, not, I'm sorry. L. Sorry about that. And En is 1 over L, alpha F plus beta G of X cosine N pi Lx dx. Okay, and again, bilinearity, right, of the definite integral. So this is cosine M pi divided by Lx dx plus beta 1 over L G of X cosine M pi divided by Lx dx. Okay, and so this is alpha An plus beta Cn. Okay, and finally, you can check that for Hn 1 over L alpha F plus beta G X sine M pi divided by Lx dx. Okay, and we have, again, by linearity of definite integral, okay, so this is alpha Bn plus beta Dn. Okay, so this is our proof for that. Okay, now, okay, so now the last topic is that consider a function f of x defined on the interval from 0 to L. Okay, so it is not periodic function, just a function define a finite cross interval. Okay, define a finite cross interval. Okay, and which satisfy the required condition in the representation theorem, in theorem 11.1.2 over the interval. Zero L. Okay. So that means that f of x is piecewise continuous over this finite cost interval. And it has a left-hand derivative and a right-hand derivative at every point in this finite cost interval. Okay? Now, it is possible. So now we want to represent f of x as a Fourier series by extending. Okay, so but we want to represent f of x over this cost interval, right? To be a Fourier series like this one. Okay. And it is possible. Okay. So by extending f of x into, okay, so we will extend f of x into, okay, a periodic function. Okay, so we can all right, so we want to represent as a Fourier series by extending into a periodic function. Okay. Now, the intuitive way, the direct way, the straightforward way, so is that if we do so, okay, by regarding, okay, so by regarding f of x in 0 to L as in a period, all right, of a periodic function. Okay, with a period L. So like this one. Originally, we have a function, okay? So for example, we have a function okay? Originally, we have a function like this one. So this is f of x from 0 to L. Now, we may regard this function as a period, within a period of a periodic function with period L. So in this way, we will have so now Okay. Not perfect. Okay. Okay. Now, in this case, we have to modify a little bit. Okay. Why? Because that in general, the function has different value at 0 and L, right? In general, they may have different value at L. So that we can do something that, for example, we keep this one, but here we open it. Okay. So there are many other ways, okay, to do it. Okay. This is one selection, right? One selection. Okay? One select. This is one possible selections. Okay. So this is g of x. Okay? G of x. So now g of x is a periodic function. Okay? So it is a periodic function with a period L. Okay. And the f of x is equal to g of x when x is in, okay, here. Okay. So we let the L to open. Why? Because that they are different. For g of L is this value, but f of L is this value. So they are different. Okay? So then they may be equal. So they are equal almost everywhere. Almost for all x. Okay. Okay. So but in this way, right? So in this way, right? The Fourier series expansion of f of x would have A0, A1, B1, A2, B2, AN, BN, okay, as coefficients. Okay? So that means that the Fourier series expansion will contain cosine term and sine term together in general. Okay? Okay, so and contain both cosine and sine terms. Okay. Okay. So this is one way to do it, but we can simplify the Fourier series expansion by using, right, first even periodic extension, say f1 of f. Okay, and maybe I use G. Okay, G E. Okay, as right. So the way is that G E x, okay, is equal to f of x for x from 1 to L, and also equal to f of minus x when x is equal to 0. Okay, so we construct an even function, right? So the construction is here. The even function is like that. Originally, we have, say here, right? Now the construction is now we do the mirror image here. Okay, so the period becomes 2L instead of L. Okay, and so now we have that. Okay, so this is f of x, and we have a g even function of x here. Okay, so we construct. So this is an even function. Okay, this is an even function. All right, and so that g x, well, n from 0 to infinity, a n, okay, and the cosine m pi L of x here. Okay, cosine m pi L. And because that this Fourier series expansion it represents the whole periodic function. Okay. Okay, and the GE x plus 2L equal to GEX. Okay, so this is just one period of the even periodic function. Okay, and the AN A0 it's a okay, so that this is so you can see that GEX, okay, plus okay, and when x is from 0 to L, this is f of x. And in this range, this is f of minus x dx. Okay. Okay, and by change of variable, then this integral is the same as this integral. Okay, so finally you have dx. Okay, so again, because we are given f of x over 0 to L, right? Only this range. So the coefficient A0 can be obtained by this integral over from 0 to L divided by L. Okay. So this is the AN for A0. How about the other? And for n greater than or equal to 1, n is equal to okay. So you can compute and this is even function. This is also even function. Okay. All right. So this is all equal to from 0 L. And this has become 2 f of x because in this range from 0 to L, this part Gex is equal to f of x. So again, you can compute the coefficient. So to this way, the original function is in a half range, right, of one period, and the representation, can be becomes to this one, and so that f of x becomes to an cosine n pi lx or x in 0L. Okay, so that means that the Fourier series, this one will converge to the half of the right inverse, right limit, right hand limit and left hand limit, and they will equal when f is continuous at x. Okay, so we have this conclusion. All right, and I can't finish the other part. So the second is add. The second is add periodic extension. And GO of f. Okay, and by doing that, G add of x is equal to f of x when x is in we specify minus f of f minus f of x. So minus f of minus x, okay, for, okay. So we construct that equality, all right, and for integral multiple of L, right, we left it open, okay, we let it open, okay, we let it open, okay. So in this case, and the G0x plus 2L is equal to G of x, all right, and G of n k L can be arbitrarily defined. Okay, for k in Z. Okay, so they can be arbitrarily defined. And sorry. Okay. All right, and so that G0, well, going to Bn sine n pi L x. Okay, n pi L x. And with Bn equal to, let me write it down. Okay. So we have this expansion. So now we are able to use the sine series. Okay. Right. So there are two different representation for the f of x. Okay. And so this is implies that the f well goes to okay for x in 0 and L. So this is called the Fourier sine series. Okay, the Fourier sine series, and this one is the Fourier cosine series. So the same function, all right, can have three different representations. One is by regarding as f of x as one period of a periodic function. So the period is L. And I didn't write it down because that it involves cosine and sine terms. So in practice, we usually use Fourier cosine or Fourier sine representation because it's much more simpler, okay, for the representation. Okay. So I have to stop here, right? And I'll see you next week. Okay. Okay.